Here's a positive point charge, proton, right? Something like that. And I'm looking at various points along a path that's moving away from the proton. And the electric field here points in that direction. But as I move further away, what happens to the electric field? It goes down, right? The magnitude gets smaller and smaller. So we have, and it's continuously getting smaller, right? The electric field of the point charge, the magnitude of it is 1 over 4 pi epsilon 0 q over r squared. So the bigger the distance, the more the electric field decreases. And so it's decreasing constantly with distance, right? So if we wanted to find the potential difference from A to B in this case, and we're moving along a path that's along a region where the electric field is not constant anywhere. It's not uniform anywhere along that path. What could we do? Based on what we've just done, how could we come up with a strategy for dealing with this? Take an integral. So what is an integral? What do you mean by an integral? Okay, so we're summing up a change over an infinite number of small pieces. Okay, since I can't draw an infinite number, let me draw a finite number of small pieces. Okay, there's a little piece of the path, and there's another little piece of the path, and there's another little piece of the path, and there's another little piece, and so on and so on and so forth, right? Well, I can use basically the same strategies we did before. If I make these little pieces of the path small enough, I can approximate the field to be uniform along that part of the path. Okay, it's not, but it might be. If it's short enough, it doesn't change much. And then over this part of the path, the field is approximately uniform, or at least constant in magnitude and direction over that path. And it's different than this one, but we can treat it as constant. And then it's approximately constant here, but different than it was before. So if I'm breaking it up into little pieces, I can do exactly what we did before and say that VB minus VA is going to be negative E1 dot delta L1, okay, minus a negative or a minus E2 dot delta L2 minus however many pieces we have, pieces of the path that we have. So in other words, we're summing up negative E sub I dot delta L sub I, if we're going from I being the counter that goes from one to the next. But of course, if we go to the limit where those delta L's are getting smaller and smaller and smaller, then this becomes, in calculus language, an integral, right? A summation of very small pieces, okay? And so we write this as a summation of E dot dl, okay? So this is what is called a path integral, okay? An example of a path integral. And this is the most formal relationship between change in potential and the electric field, okay? This works all the time, okay? It doesn't matter if it's uniform, non-uniform, what have you. This is the most general relationship between electric field and potential difference, and we're going from A to B here. If you want limits on the integral. So what does this mean? A path integral. We're taking a dot product of a vector and a little piece of a path vector in that integral, and so it really is the same as saying the sum of E sub x dx plus E sub y dy plus E sub z dz, okay? You can think of this dl path element just like we thought of the delta L path element. It has some magnitude, it has some direction, has components, and we can just break it up into components and then do the dot product and sum it up, okay? So let's try it. Let's try an example for this particular case. We have a point charge, and I'm going to, so I'm placing my point charge at the origin here. So this is y, and this is x, okay? And the magnitude of the electric field is 1 over 4 pi epsilon 0, q over r squared, okay? Now, just to simplify things for right now, I'm on the x-axis, so I'm going to call the distance x, okay? And that means if I'm on this particular x-axis, I can say that the electric field in this case is 1 over 4 pi epsilon 0 q over x squared comma 0, right? It's just what the value of the electric field would be anywhere on the x-axis, right? It would have a 0 y component, 0 z component, and the distance would just be x, right? Are we okay there? So what do? We have a electric field vector. We have a path. So we need to take this integral, right? Say VB minus VA is negative of the integral from some initial x value. Call this x initial at point A. Call this x final at point B. X initial to x final. We have 1 over 4 pi epsilon 0 q over x squared. Well, let's write it out completely. 0, 0 dotted with dx, dy, dz. Okay. And then when I take the dot product between the vector and the path element vector, all I'm going to get is just the x term, right? Q over x squared dx plus 0 integrated from x initial to x final. Okay. Okay, so let's do it. What in here is a constant? Everything but x, right? So I can bring the 1 over 4 pi epsilon 0 out. I can bring the charge out. I have the negative sign outside. I'm going from x initial to x final. And I'm integrating, let me write it this way, x to the negative 2 power dx, right? And the indefinite integral gives me what? You integrate x to the minus 2 and you get what? What do you get? Negative x to the minus 1. Okay, negative x to the minus 1. All right. And I'm evaluating from x initial to x final. So in other words, negative 1 over x. Let me write it that way. Okay? Lost a negative sign. That's easy to do. So, well, let me cancel these negatives out. That cancels that. And we finally end up with 1 over 4 pi epsilon 0 q 1 over x final minus 1 over x initial. Okay. We should check it. We should check to make sure. And VB minus VA. And really to be consistent, I could say this is final and this is initial, but whatever. We should check to see if the sign is correct. Now, if this is a positive charge, my path goes from A to B. I'm going in the direction of the electric field. So I expect my delta V to be what? Negative. Expect my delta V to be negative. Okay. Is this expression negative? Well, that's a positive number, right? The charge is a positive number. We have 1 over a large distance minus 1 over a small distance. So, for example, this could be 1 over 10 meters minus 1 over 1 meters. Is that going to give me a negative? Yeah, that's going to work. So we are going to get the correct sign with this. It works out. Okay. So we've got then a result for the potential difference due to a point charge between two points in space. And in fact, we did it on the x-axis. But it turned out to be even more general result, because I could have thought of, for instance, 2 points A and B that don't lie on the x-axis. Maybe they're still collinear, okay, with the point charge, but they don't lie on the x-axis. Well, it doesn't really matter, because again, I'm doing the same sort of calculation just along a straight part of the path, and so I can just call that distance away, as we usually do, r, and I could write then VB minus VA is equal to 1 over 4 pi epsilon 0 Q 1 over R final. Well, again, this is final. Let me call this R sub B minus 1 over R sub A. Okay. All I'm doing is changing the role, changing the name of this distance variable, just calling it R, what we usually call it, instead of X. Well, okay, but what if we had A here and B was maybe over here? They're not along the same path. So maybe A is there and B is, let's redraw it. Here's the positive charge, here's A, but B is down here. Will we get the same result? Any guesses? Turns out we'll get the same result. And the reason is, notice what the formula is telling us. It only tells us about the distance away, okay? We could pick a path here. Well, if I picked that path, that would be a little bit tough, okay, because the electric field is going to be pointing radially away from the point charge, but the path is going to be some funny direction. So let me choose this path instead. Let me go from A to a distance here that's the same distance away as B from the point charge. Okay, so I'll call this R sub A. This distance is R sub B. And this distance is R sub B. Okay, so I go from here to here, and we get exactly what we worked out before. Then let me pick a semicircular or a circular arc that goes from this distance to this distance. It's the same radial distance away, but I'm just traveling along the arc of a circle. What is that part of the path going to give me in terms of the potential difference? Why is it going to give me 0? Say it again. You're always perpendicular to the field along that part of the path, right? The electric field points directly away from the point charge. And your path here, everywhere along that little arc of a circle, is perpendicular to the electric field, right? So path independence says if I choose one path that gives me this result, then all of them are going to give me this result. So this works out no matter where the 2 points in space are. If you want to find the potential difference just due to a single point charge, that's the result. Okay. I wouldn't worry too much about memorizing this, but you should know how to do this type of calculation. Okay. If you're given a non-uniform field and you're given 2 points, you should know how to set up, or at least at very least set up the integral and how to calculate it. Okay. And then if it's a simple enough case, we can actually calculate and work out the integral. Okay. Questions? Let's see if we have a question. We'll come back to this one. Let's do this first. So this is just an application of this result we just talked about. We have a 5 nanocoulomb sphere, uniformly charged sphere. So say it's like a ping pong ball with a positive 5 nanocoulombs rubbed over the surface. It's uniformly charged. Point B is at a distance 2 centimeters from the center. Point A is a distance 5 centimeters from the center. What's VB minus VA? Okay, so where's the path going from? It's from where to where? Where's the path start? Starts at A, right? We're going final minus initial, so the path direction is up, okay? So keep that in mind. Check the sign of the result when you're done to see if you are getting the correct sign. Okay, so most of us are getting number 1, which is correct, I believe. The again, we can check the sign, right? Because the electric field is pointing down, right? It's positive charge. The path is going up. So if the field and the path are in opposite directions, we should get positive. We should get a positive change in potential. Okay, so that's only 1 or 3, basically. And you can plug it in. Okay, you're given, you know the constant, you know the charge. You know distance B is 2 centimeters, 0.02. Distance A is 5 centimeters. Should work out to be, if you plug all of it into 1,350 volts. Okay. Okay, it's just, we have the results. We could just plug it in. We okay? Questions there? Yes. A is the initial in this case because we're always measuring final minus initial, right? So if it says VB minus VA, B is the final position, A is the initial position, right? The diagram showing the distance from the center to location A is 5 centimeters. So maybe the diagram was misleading, but this 5 centimeters was referring to this whole distance. Yeah, that whole distance. That's right. If B was 5 centimeters from A, then yeah, the final distance would have been 7 centimeters in that case. Okay. Okay.